Howdy folks. So in the last video we started the idea of Lewis structures and how to go about doing them. In this video I'm going to go through the basics of most simple inorganic Lewis structures. Inorganic just simply means that they're not hydrocarbons. They are not going to follow the organic framework. A lot of these guys, they can still be neutral. Some of them will be charged, but they'll follow a different set of rules from the ones we finished off last video with. So with that in mind, let's go ahead and get started. Okay, these are the 7 rules I'm going to use in all of my structures. We have to keep in mind that all S and P electrons should be accounted for, and that all octet and duet rules are obeyed. So the first step is always sum up all of the valence electrons present. Knowing how many electrons you have to work with is going to be the most important thing, because you'll know, am I missing some electrons or to add some electrons? You can draw it, you can wing it, but without summing them up, you could be well off. You could be wrong. In organic structures, we didn't need to do this because they follow a very, very regular rule. These guys may not always follow the rules, so we always need to do this. Sum up the valence electrons. The second rule is that we will just select a central atom. Most of these structures are going to have one central atom, and so we don't need to worry about like multiple centers. We're going to have one center atom, then everything's going to be bound to it, or just about everything. Now, the central atom is typically going to be the first atom present in a chemical formula, except for hydrogen. It's typically going to be the atom that can make the most number of bonds. Remember, carbon makes 4, nitrogen and nitrogen-based elements make 3, oxygen 2, and halogens 1. So carbon is typically already going to appear first in most formulas, but if it doesn't, it's still probably the center. Now, once we've placed all the other elements around the center, we are going to make single bonds. This is the key thing. Make single bonds before you do anything else. Make 2 single bonds from the center atom to all of the outer atoms. If you have more atoms than 4, it might be rearranged in a different way. If you're making 5 bonds to the center atom, you might be wrong. So just think about it first. In these first set of structures, we're only going to have at best 4 atoms around the center atom. So we're using 2 electrons apiece. So from our summed up valence electrons from step 1, we're going to take 2 electrons and make single bonds. Now, to any of the outer atoms, we are going to add electrons to them to give them an octet or a duet. So we're going to take electrons from our total sum and make octets or duets. In most cases, this is going to mean 6 electrons per atom, because 6 electrons plus the 2 from the single bond make 8. Now, before we do anything else, check to see if we have any electrons left after we've given the outer atoms the octet or duet. If there is a single electron left, we will put those remaining electrons on the center atom. It doesn't matter what other situation we have, we are putting the remaining electrons on the central atom. The most common mistake I will see on Lewis structures is people go, the center atom doesn't have 8, so let's start giving it double bonds or triple bonds to give it 8, when they still have electrons left. Always place the remaining electrons on the central atom. Now, and only now on step 6, if the central atom still has less than an octet, we will shift a lone pair from one of the outer atoms. We will shift the lone pair from one of the outer atoms into a bonding pair to the central atom. So if the oxygen has 3 lone pairs and the central atom does not have 8, we will shift one of the lone pairs down. So the lone pair is lost from the outer atom and it goes into a shared covalent bond. Now the beauty of this, when we take it from the outer atom and put it to the inner atom, the outer atom still maintains its 8 electrons because it's not losing it, it's now sharing it. But the inner atom is gaining 2 electrons because it is now sharing them when they previously had none. It's changing the electrons from they all belong to the outer to it's shared outer and inner. The often forgotten last step involves testing it, making sure that, yes, indeed, all electrons are accounted for, that all of our octet duet rules are obeyed. If you haven't done this, you can easily make simple mistakes. Math errors abound. So let's look at these guys. CO2 NH3 HCN BH3. So I'm just writing them down so we can now look at them. With that in mind, let's go to the dot cam. Step 1, as always, is add up our number of electrons. Carbon has 4. It is group 4. Oxygen has 6. It's group 6. There are 2 oxygens. So how many total electrons? 6 plus 6 is 12. 12 plus 4 is 16. Okay, 16 valence electrons. Step 2, find the first atom. What's a C? Put an O on either side. You could put them top and bottom. You can put top and right. It doesn't really matter. Lewis structures do not have to be pretty. They have to be show bonding, valid bonding. So I'm going to take 2 electrons to make a single, 2 electrons to make a double. And so we used 4 of our electrons. We have 12 remaining. Now, oxygen has 2. It wants 8. So we need to add 6 more electrons. 1, 2, 3, 4, 5, 6. This oxygen has 2 and it wants 8. So it wants another 6. 1, 2, 3, 4, 5, 6. We have 0 valence electrons left to place. So we look. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. We have 0 electrons left to place. We cannot place any more on the center atom. So, with that in mind, what can we do? Well, we have outer atom lone pairs. We are going to take them away and move them to the center atom. There's 2 different ways to do this. One is technically more valid, but if the question just simply asks for draw a valid Lewis structure, both of these are equally valid. I could take 2, make a double bond, and then another 2 and make a triple bond. And I could do it from the other side as well, but now it's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Still 8 and 8 and 8. The better answer in this case is I can take 1 set from here and 1 set from here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Both of these structures, everybody has an octet. All 16 electrons are accounted for. It is valid. NH3. N is 5. Each H is 1. We have a total of 8. The first non-hydrogen atom is N, so we'll put N, H, H, H. Make single bonds. 2, 4, 6. We have duet, duet, duet. That's all they want. So the remaining electrons must go on the central atom. Now it has 1, 2, 3, 4, 5, 6, 7, 8. Stable. We don't need to make any double bonds. It is stable. So we can stop there. We have 8 electrons, octets, duets all around. We are good. So, first non-hydrogen element. 4, 5. We have a total of 10 electrons. So I'll put the C with the H and the N. We're going to make 2, 4. Means 6 are left. We put it, this guy already has a duet, so it's good. So we're going to put 6 on him. 1, 2, 3, 4, 5, 6. We have 0 electrons left. And so 1, 2, 3, 4. Now, we can only take from lone pairs. We cannot take from bonds. So hydrogen has nothing to give. So what are we going to do? We're going to take 1 set from here, 1 set from there, and now suddenly we have 1, 2, 3, 4, 5, 6, 7, 8. And this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. It's good. And boron. Ooh, boron has 3. Hydrogen has 1, 1, and 1. This guy has 6. When we draw this guy, H, H, H. 2, 4, 6. We've used up all 6 electrons. This is one of those weird exceptions where we cannot give boron 8 electrons. Boron cannot get 8 because there's not enough electrons to go around. And so it is stuck at 6. Occasionally that happens. I'm thinking of one fresh straight off my head. Let's say, something really easy. 2O. 1 plus 1 plus 6. 8 electrons. O is the first non-hydrogen element. We put O. H. H. We subtract out my 4. We have 4 electrons left. Where do they go? They go as lone pairs. 1, 2, 3, 4. We have 0 electrons left. 2, 2, 8. Happy. And let's see. I'm trying to think if there's anything else. Think of right off the top of my head. Whew. Yeah, we'll do. And was H2N. Cl. Okay. 1 plus 1 plus 5 plus 7. Add those up, 7, 7. You have 14 electrons. Okay. N can make the most bonds. It appears before Cl. Cl, H, H. 2, 4, 6. We've used up 6. We have 8 left. 1, 2, 3, 4, 5, 6. We have 2 left. This guy has a duet, and octet, so we have to put the remaining 2 right there. And now he has 1, 2, 3, 4, 5, 6, 7, 8. We are happy. We have to put any remaining last electrons on the center atom. And if it has an octet, you could probably stop right there. But okay, let's go back to the PowerPoint in the meantime. So all that assumes uncharged. Uncharged. We're neutral. Well, what happens when we start to get charged ions, such as polyatomics? If we draw a polyatomic ion, how do we imagine that? Polyatomics are charged, but they are made up of a series of covalent bonds. Whenever the structure is charged, we must add or subtract valence electrons from the total electron count. So if it is negatively charged, we are adding electrons. Remember, electrons are negative. So if it's negatively charged, we're going to add that many electrons to add up to the charge. If it's positively charged, we will remove that many electrons from the total count. And if you do that, now we just have more electrons to play with. If you were to draw that Lewis structure, typically what they would have you do is put that a charge structure in brackets and then put the superscripted charge above the brackets. You do not necessarily have to label the which atom is negatively charged like I've done in the picture. We typically would just bracket and let people know that it's hypochlorite and not chlorine monoxide. They want to make sure to specify the charged structure versus the uncharged structure. So NO2 is nitrite. NO2 neutral would be nitrogen dioxide. Those are completely different structures, and thus we need to emphasize that in the Lewis structure by showing that it's charged. One other thing to note is the concept of resonance. As we draw our Lewis structures, it is often possible to draw more than one given arrangement of double bonds. I'm not saying like a whole new Lewis structure, but I'm saying you could, like in the example of CO2, we could take a pair of lone pairs from each oxygen, or we could take two pairs from a single oxygen, whether that be the right oxygen or the left oxygen. These are each unique structures. However, they're also not unique because they will share a resonance between each other. That basically a resonance structure is one that differs only in the placement of the multiple bonds and the lone pair sets. So each individual structures are called resonance structures. And why this is important is that when a structure has resonance, and we have multiple resonance structures, what we see is not just one single structure that is unique. You see a mixture of the two. The example I have up there is ozone. O3. Ozone, you could draw a structure that we have oxygen 1 is double bonded to oxygen 2, which is single bonded to oxygen 3. Or you could draw oxygen 1 is single bonded to oxygen 2, which is double bonded to oxygen 3. Now that may look like just a pedantic argument of who's double bonded to whom, and you can maybe even say, oh, I could rotate it so oxygen 3 now looks like oxygen 1. And that is true, you absolutely could rotate them. But the thing of it is the atoms are not rotating to superimpose themselves on each other. They are distinct structures. Distinct structures that if you were to label oxygen 1, label it by making it heavy oxygen. You bombard it with neutrons so it absorbs a neutron and becomes O17 or O18. So you can physically distinguish it from its twins. You will see that both structures exist, that you'll get a combination of structure 1 and structure 2. That double bonds are shorter than single bonds, and that you'll see one structure has a short double bond to the heavy oxygen, and one structure has a long single bond to the heavy oxygen. And what we see is if we analyze this enough, we get a structure that is not actually double bonded or single bonded. It is a mixture of the two. You get a bond that is actually experimentally between a double and a single bond. This is because there is a delocalization. Breaking that down, when a bond is stuck in place, it is called localized. It means these electrons, even though they're moving around an electron cloud, are stuck in this region of electron density, and they're going to be found mostly in between these locations. It's like if you have a bestie who, like, you're always at their friend's house, or she's always at your house. It doesn't matter if your mom goes, "Where are you?" Well, she knows, oh, I better call the bestie's mom because she's probably over there. Well, it means they're localized in one location. Well, when electrons are delocalized, they're capable of moving, swapping around, going to a different place. In this case, maybe you have a couple friends, so if you're not over here, you could be over there, and maybe if you can't find you at either place, maybe you're in transit from one location to another. That these electrons are capable of flipping and flopping from one location to another. And this will have implications later on. But basically, this transfer is so fast that we get a averaging of the two structures. We get what's called a resonance hybrid, which is what we see in most cases, where it's moving so fast you don't see where it's at. It's like the Flash, like doing a bunch of side steps back and forth, jump back. He's moving so fast, he's neither, if you shoot at position 1 or position 2, you're not going to hit him. You kind of just have to aim in the middle and try to get him while he's jumping back and forth. So you get like an averaging between the two. This resonance hybrid is a more accurate interpretation of the molecule. The only way you could stick it in one or the other is by rapid cooling. If we cool this down, well, not really rapid cooling, but cooling this structure down to an incredibly low temperature, what that does is it slows down all movement. And it will slow down electron movement. And we can actually slow things down enough so we can see each unique structure rather than the average of the two. But so that is possible only with cooling the structure down, thus slowing down its movement. Now, let's put these things together with electronegativity. In the previous chapters, we talked about ionization energy and electron affinity. Ionization energy being the energy required to remove electrons. Electron affinity, the ability to attract new electrons within a neutral atom. Well, electronegativity is a similar property, except instead of being within a pure atom, it's within a bond. Electronegativity combines these two properties within a covalent bond. If an atom has a high ionization energy and a high electron affinity, meaning it's hard to lose electrons and it's easy to gain electrons, it has a high electronegativity. If they have low ionization energies and low electron affinities, it's usually they have a low electronegativity. Electronegativity is the ability of a bonded atom to attract the shared electron set through the bond. So when we imagine the covalent bond, the electrons are being shared in that center. Well, the thing of it is they're not always being shared equally. They're not always being shared equally. So that's not always perfectly in the center. They might be moving to one side, towards one atom or the other. So it all depends on the ability to strongly pull them one way or another. Think of it back in that example of the besties. If you and your best friends have the same things at each other's houses, you could be found at either location without a problem. But say your bestie has the newest game system, like a PlayStation 5, and always has a unlimited supply of ho-hos and like RC Cola, you're probably spending most of your time over there instead of at your house. So you always you look at the electronegativity to see where the electrons are spending their time. One of the things to note is fluorine is the element with the highest electronegativity. Then as we move outwards, we have oxygen, and then chlorine and nitrogen are about the same, and then carbon and sulfur are about the same, and boron, and we have hydrogen and phosphorus are about the same. Boron and arsenic are about the same. So it's typically electronegativity increases as we go up and to the right. One thing to note is some of the early noble gases will not have electronegativity. They will not like to make bonds. But krypton and xenon can make bonds. Are they particularly good at it? No. But they can. Generally speaking, though, the greater the electronegativity, the greater the pull on the electrons, the more likely it to have lone pairs. The atom with the lowest electronegativity is often the central atom. The lowest electronegativity is often the central atom, which is, remember, the lowest electronegativity is the guy with who's most positive. The guy that's usually the most positive gets treated like the cation. The guy that's treated like the cation is always comes first. So the lowest electronegativity atom is almost always the central atom. If you have a choice, if I had S's and O's, S is going to be center, O is going to be outer. O is going to have more lone pairs. S's and N's. S is probably going to be center, N is going to be outer. So, but S and P, S is going to be outer and P is going to be center, just based on electronegativity. So, with that in mind, this will bring us to the last major concept before we do some practices. Formal charge. If you have multiple resonance structures possible, what is to distinguish resonance structures? They may not all be equally stable resonance structures. Some may be better than others. One way to figure that out is by a process called formal charge. Formal charge is just a type of electronic bookkeeping. We're going to take into account the electrons that should be there versus the electrons that are there. So a formal charge is the hypothetical charge you put on an atom in a Lewis structure based on the absence or presence of electrons compared to the starting valence electrons. So each atom has so many valence electrons. When we start to make bonds, those bonds are going to be accounted for by those valence electrons. Any lone pair is accounted for by those valence electrons. Anytime we have less valence electrons around the atom than when we started, we adopt a positive formal charge. Anytime we have more valence electrons around there than when we started, we have a negative formal charge. And so what we're going to do is we're going to count all the lone pairs around the atom and half of all the shared electrons. Why half? Because the bonds are assumed to be a 50-50 contribution. And we're going to compare them to the atom's valence electrons. If they're the same, it's said to be zero formal charge. One thing to note is that all formal charges on an atom should add up to the atom's overall charge. So if the atom is neutral and you have a formal charge of positive, you must also have a formal charge of negative, because plus 1 and minus 1 cancel out. But in general, the most stable structures that exist will have small to no formal charges present. If you can draw a structure without any formal charges, it is probably the stable resonance structure. When they have to have formal charges, because there's no way to draw it otherwise, anytime you can give the negative charges to the atoms with the highest electronegativity and the positive charges to the atoms with the lowest electronegativity, you get a more stable structure. So if you have to have a formal charge Try to put the negatives on the electronegative and the positives on the less electronegative, the electropositive in this case. So we will finish up with these, and there might be another practice, but we'll start with these guys first. Okay. I've put a challenge one on here, as we'll see in a minute. Duncan. So let's start with NO3. NO3 is as follows. N5 O6. There's 3 of them, so that makes 18 plus 1 because it's -1. 18 plus 5 plus 1 is 24 electrons. Now N comes first, and it's the can make the most bonds, and it's the most in the center. Most bonds, least electronegative. So let's put the O. Okay. 2, 4, 6. We're down to 18. Each oxygen wants 6, so that uses up the remaining 18. So I'll put that in. Now, no electrons left to place. I'm going to, nitrogen has 2, 4, 6. I'm going to take 2 away from here and put that as a double bond there. Now let's look. This guy is 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Now I'm going to call that O1, O2, O3. Now let's look at the formal charges of this structure. Let's look at the formal charges of this structure. We have O1, O2, O3, and then N. There should be 6, 6, and 6, and 5. Now, O1 has 1, 2, 3, 4, 5, 6, 7. O2 has 1, 2, 3, 4, 5, 6, 7. O3 has 1, 2, 3, 4, 5, 6. And N has 1, 2, 3, 4. So what are the formal charges? Are -1, -1, 0, +1. So put a negative, a negative, a positive. They should add up. -1, -1, +1 adds up to -1, which matches that. Is there another resonance structure we can draw? I'm not going to go through all the steps, but yes, instead of taking that lone pair, I can take from that lone pair. So we can draw this out as negative, positive, and negative. And we can draw one more structure where we take it from that lone pair. And so we have a third resonance structure. Even though we have 3 formal charges in this compound, it is still relatively stable because it is able to resonate these charges around. When it resonates those charges around, it stabilizes the structure by a little bit. So no single oxygen has a full charge. Now the nitrogen still keeps the positive charge, but no single oxygen contains a full charge. S. This guy has 6, C has 4, N has 5, plus 1. So we have 16 electrons. I'm going to put C in the center. You can make the most bonds. S, N. Let's make 2 bonds. That's make minus 4. That's 12. Boom, 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 boom. Hey, hey, hey. That uses up all 12. We have 0 electrons left. Carbon has 1, 2, 3, 4. It needs 8. There are 3 possible structures. Let's draw them out. Structure 1. Structure 2. I can do it the other way. I'm going to skip some of these steps. And structure 3. Where I'm possible to take a lone pair from each set. So, sulfur should have 6, carbon should have 4, nitrogen should have 5. We have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3, 4, 5. 0, 0, negative 1. So this structure has a negative on the sulfur. This structure, 6, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. And then 1, 2, 3, 4, 5, 6, 7. We have negative 2, positive 1, 0. This one has a positive and 2 negative. And this structure has 4 minus 4, 6 minus 1, 2, 3, 4, 5, 6. And 5 minus 1, 2, 3, 4, 5, 6. 0, 0, negative 1. So just by looking at these 3 structures, this guy is similar to this guy. The only difference is we put the negative 1 on the S versus negative 1 on the N. This guy is the worst structure. It has 1, 2, 3 formal charges. This guy has 1 and 1. So how do you differentiate? The electronegativity of sulfur is 2.5. The electronegativity of N is 3.0. We put the electronegativity on the atom with the highest we put the charge on the atom with the highest electronegativity. So this guy is the best structure. Last one, N2O. 2 N's and 1 O. This guy is actually, this guy would be better written as NNO. So one of these N's is in the center. I'll draw the NNO. We make single bond, that's 4, 12. 1, 2, 3, 4, 6. 1, 2, 3, 4, 5, 6. Used all of them up. We have a similar situation from the thiocyanate, except it's neutral now. We can draw 3 resonance structures. Let's draw them. So let's start with 1, 2. We can draw 1, 2, 3. Please note that the center nitrogen is not gaining more lone pairs, it's just gaining more bonds. And then we can draw this guy. Okay, let's look at these pairs. How does this structure differ from the thiocyanate? So we call that 1, 2. So N1, N2, 5, 5, 6. We have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. And then we have 1, 2, 3, 4. So we have -2 plus 1 plus 1. So positive, positive, -2. That one is probably the worst structure. Once again, 1, 2, 3, 4 positive charges. Let's try this again. 5, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 0 plus 1 minus 1. This is probably the best structure. We put the negative on the oxygen, and we'll see why in a second. Let's look at the last structure. 5, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So no matter what, the center atom keeps a positive charge. But in this case, the N adopts the negative, N being 2.5. And the O, actually, sorry, it's 3.0. And O should be 3.5. We want to give the atom with the largest negative, the largest electron negativity, the largest charge. And that's what we see right there. Okay, last slide before we end this video is just a quick summary of all that we've talked about. So now, when we think of our valid Lewis structures, these rules need to be taken into account. The best Lewis structure should have all valence electrons from all atoms accounted for, adjusting for ionic charge. All octets and duets on all atoms. It should have the smallest formal charges, all formal charge of whose sum should be no greater than the overall charge. And you should try to draw all reasonable resonance structures whenever available. But that's some rules to take into account when we're doing these. That's where we'll stop for now. We'll finish this chapter up with the next video.